I'm Adam from RFOXiA from our real lab. Today we are asking why your GNSS module has absolutely no idea where it is for the first 30 seconds after it powers on and what that actually costs you in a real application. Now enjoy our new track. Let's talk about time to first fix. It gets abbreviated as TTFF. It is one of those specifications that appears on every GNSS data sheet, usually buried somewhere after the accuracy number and the operating voltage range because nobody wants it to be the first thing you read. TTFF is the amount of time between your module receiving power and your module producing a valid position coordinate. During that interval, your device knows nothing. It has a receiver, it has an antenna, it has a chip that is theoretically capable of telling you exactly where you are on the surface of the Earth within 1.5 meters, and it is producing no useful output whatsoever. It is just listening. Now, why does this take time at all? The short answer is that GNSS satellites do not simply announce their location. They broadcast a continuous stream of navigation data, their orbital parameters, their clock corrections, their health status, and a receiver has to download and decode that entire dataset before it can calculate a position. This data is called the almanac and the ephemeris. The almanac is the course map, which satellites exist and roughly where they are in the sky. The ephemeris is the precise dataset, exactly where each satellite is right now to the degree of precision required for accurate positioning. The ephemeris data for a single satellite takes approximately 30 seconds to transmit at the signal data rate. If your receiver has no stored data from a previous session, it has to download the ephemeris from scratch for every satellite it intends to use. That is a cold start. Cold start TTFF on a cheap GNSS module is commonly between 30 seconds and several minutes, depending on signal conditions, sky visibility, and the quality of the receiver. This is the number that nobody leads with. The accuracy spec is 2.5 meters. The fix rate is 10 Hz. The TTFF is, and we will get to that later. For a lot of applications, this does not matter. If you are building a weather station that sits in a field and streams sensor data, your device powers on, waits 90 seconds, gets a fix, and runs for weeks. The TTFF cost is essentially zero against a multi-week deployment window, but there is a large and growing class of applications where TTFF is not a minor footnote. It is a primary constraint. Consider a drone. A drone does not sit on a launch pad for 2 minutes while the pilot waits for the GPS to sort itself out. In some operational contexts, a drone needs to know its position the moment it lifts off. Autonomous flight modes, return to home, waypoint navigation, geofencing, all depend on a valid GPS fix. Without that fix, the drone is operating on inertial data only, which drifts. It is navigating blind, and the longer the blind period, the more drift accumulates. Consider a vehicle tracking module. The device may be powered intermittently, turning on when the vehicle starts, going into sleep mode when the vehicle parks. Every power cycle is a new TTFF event. If your module takes 45 seconds to achieve a fix, you have a 45-second gap in your tracking data every single time the vehicle restarts. In logistics, in fleet management, in any application where position continuity matters, that gap is not acceptable. Consider a wearable device. A runner starts their workout, they look at their watch. The GPS is still searching. This is a well-known consumer frustration. The underlying cause is TTFF. There are design approaches that reduce TTFF without requiring a cold start every time. Assisted GNSS, AGNSS, preloads the ephemeris data from a server over the internet, eliminating the 30-second download requirement. Hot start, where the receiver retains its last known ephemeris in memory, can reduce TTFF to under 1 second for a receiver that was recently running and has not moved significantly. Warm start sits in between. The almanac is stored, but the ephemeris needs to be refreshed. A cheap module may advertise these capabilities and implement them poorly. The chip may be adequate, the supporting hardware, the crystal oscillator quality, the antenna design, the RF filtering determines how quickly the receiver can acquire and lock onto satellite signals under real-world conditions. A weak receiver that struggles to hear satellites in a partially obstructed sky takes longer to achieve a fix regardless of what the datasheet says about AGNS support. This is where receiver sensitivity comes back into the picture. A module with strong sensitivity, meaning it can acquire weaker signals, gets to a valid fix faster because it is not waiting for a satellite to be in a clear, unobstructed position before it can decode the signal. It can work with the signals it has. The MultiNav Pro Plus achieves a first fix in just 1 second, so your device knows exactly where it is the moment it wakes up, not sometime next week. 1 second. That is a hot start figure under nominal conditions. The u-blox MIA M10Q chip that powers this module is designed for exactly this performance. It supports concurrent reception across GPS, Galileo, GLONASS, and Beidou simultaneously. More satellites means more signal diversity. More signal diversity means faster acquisition. Faster acquisition means a shorter TTFF. The integrated chip antenna on the MultiNav Pro Plus is not an afterthought. It is sized and tuned to the frequencies that GNSS signals occupy. L1 band, 1575.42 MHz for GPS. The RF microstrip filter on the board reduces interference from adjacent electronics that would otherwise compete with the satellite signal and slow acquisition. At 18 Hz fixed rate, the module, so that is TTFF, what it is, why it fails on cheap hardware, and why the fixed rate and receiver design matter far more than any spec sheet summary suggests. Now let me show you the actual module. This is the MultiNav Pro Plus built on the u-blox MIA M10Q. It receives GPS, Galileo, GLONASS, and Beidou simultaneously, not sequentially. Concurrent multi-constellation acquisition is a primary reason this module achieves a 1 second first fix rather than a 30-second one. Less than 1.5 meters of accuracy, 18 Hz fix rate, and a 1 second first fix. These three numbers are related. The same receiver sensitivity that enables fast acquisition also maintains precise position tracking. Your device does not wait to know where it is, it simply knows. 26 by 22 millimeters, 25 to 30 milliamps. That is the entire power and size cost of professional GNSS performance. The efficiency comes from the MIA M10Q architecture, designed for mobile and embedded applications where battery life and board space are real constraints, not theoretical ones. UART and I2C both supported, 1.8 volt and 3.3 volt operation. This module connects directly to whatever microcontroller you are already using without a level shifter or additional conversion hardware in most standard configurations. Integration should not require a separate engineering problem. The driver library is open source, written in C, and implements the full NMEA standard protocol. Importing it into Arduino IDE takes minutes. The same library works in any toolchain that can compile C. You do not spend time writing a parser, you spend time building the application that uses the data. U-Center is u-blox's evaluation software. You can see every satellite the module is tracking, watch signal strength bars update in real time, configure output parameters, and log raw GNSS data. For validating that your 1 second first fix is actually happening, this is the tool you use. Drones, IoT deployments, wearables, tracking systems, automotive research platforms. The 1 second TTFF is relevant across all of these. Any application where the device moves, powers on intermittently, or needs position awareness before it can safely operate benefits from this specification. That density of position data is what makes fast-moving platform tracking viable. A drone moving at 60 km per hour travels approximately 1 meter every 60 milliseconds. At 18 Hz, you get a new position fix every 55 milliseconds. The position data keeps pace with the physical reality of the platform. At 25 to 30 milliamps operating current, it does all of this without being a meaningful battery drain. For field-deployed hardware where power budget matters, this is a number that deserves attention.
Constellations up above, locked in orbit, signal love. 18 fixes every second, every meter calculated. No drift, no guess, no hesitation, just the truth of your location. 1.5 meters from the truth, every coordinate living proof. GPS, Galileo, GLONASS aligned. Beidou locked exactly where I am. Precision at the speed of land. Fast-moving platform, still it holds. Signal strength that never folds. Sky above becomes a map. Every second fills the gap. Urban canyon, open field. Four constellations never yield. The sky is full of to be heard. Every satellite a compass, every fix confirmed. Nowhere on this planet falls outside the grid. 0.5 meters margin, that is all there is. 1.5 meters from the truth.